Chapter 4.6 is about similarity. So far we've been talking about congruent figures. So last time I said which ones are exactly the same, meaning they are congruent. Now we're talking about similar. So I could have two triangles that are similar, but they are not exactly the same size, okay? Or I could have two circles that are similar, but they are not exactly the same size. So a similarity transformation is a dilation or composition of rigid motions and dilations, all right? So that means that you could have a glide, and then you could have a dilation or either a enlargement or a reduction. You could have a rotation, all right? So similar figures are two geometric figures that are similar if and only if a similarity transformation that maps one of the figures onto the other. So they don't have to have the same size, but they do have to have the same shape. And if you are going to prove that two figures are similar, you must prove that a similarity transformation maps one of those figures onto the other. So that is all your notes. Yep, that's it for chapter 4.6. So let me show you a few example problems. So here, you have a translation. I wonder if I can make this a little bigger. That's better. Okay. So here you have a similarity transformation because you are going to be graphing a triangle. So we're starting with the blue one because the blue one is your original figure. And it says to translate it by adding 5 to x and 1 to y. So I add 5 to all my x's. So -4 becomes 1. I add 1 to all of my y's, and I get 2. So here's point A. And then I do that with all of those, B and C. So here I've translated this 5 over and 1 up, the entire figure. And then they said they're doing a dilation with a scale factor of 2. So it's larger than 1. So that's going to be an enlargement. So we take this triangle and I multiply each of these points by 2. So if I'm doing A prime, 1 times 2 is 2. 2 times 2 is 4. I do that with all of them and I end up with triangle ABC double prime. Does that make sense? Are you guys okay with that? All right. Okay, this is the other thing I wanted to show you. Let me make this a little smaller. Okay, so here they're going to ask you to describe a transformation that's similar. So we started out with this blue quadrilateral over here. Okay, so P, Q, R, S. And over here, it's mapped onto W, X, Y, Z. So remember, when we're describing a transformation, the P has to map onto the W because the P is the first one and the W is the first one in each of these quadrilateral names, okay? So we need to make sure that we map these in order. So if I look at where P is and where W is, I can see that there's some kind of reflection going on here. And obviously there's a dilation that is a reduction. So it appears that it is reflecting in the y-axis, okay? And then there is a dilation of a fraction. So we have to figure out what that is. And I can do that by looking at the numbers for P and W because they map up. Okay, so if I were to translate P over to this side, P is 6 away from the y-axis. So P would be right here. Okay, so P would be 6, 3. So 6, 3 became 2, 1. 6, 3 became 2, 1. Okay, so what do you think we have to multiply by in order to get 6, 3 to be 2, 1?
It's like we were missing. Oh, Kevin.
So here's the answer. Okay, so it is a dilation of 1/3. Okay, it is a reflection in the y-axis. Okay, so 6, 3 becomes 2, 1. All right, does that make sense? We multiplied by 1/3, everything by 1/3. All right, so when you're solving these, just look at them and see where you think it needs to go, and then pick a point, whichever one you want, and map it up to the point it goes on the other one. Okay, Amber, I'll go over that in a second. All right, any other questions about this problem? Okay. All right, let's see. Amber, which